And then I'll open the time for, we'll finish this. We're gonna do, there's like 3 problems that do this in Pearson. We'll do those 3 problems for examples. And then we will see if there's any questions, and that'll be it. Okay? I mean, that'll be it for the semester. Finish this up. Okay, let's suppose we have some curve here in polar coordinates. Remember, in polar coordinates, when we find a point, the point is r theta. So, we measure the angle from the positive x-axis to there, that's theta, and then the distance from the origin to there, that's r. Somehow we got to figure out how to find area inside these things. All right? Before we do that, let's review how we found area back in first semester calculus. It would have been at the end of the course if you took it here at Reedy College. In an AP class, it's closer to the middle because in AP they go all the way to April. All right? They don't have just one semester like we have here. So if we wanted to find the area under a curve, that would be between the curve and the x-axis from A to B. We break it up into rectangles. We call this a partition. All right? We break it up into rectangles that we call a partition. Each one of these intervals, this is A to x1, it's like x naught to x1. That's an interval. Well, actually, these are sub-intervals. The interval is from A to B. These little ones are sub-intervals. Anyway, I just picked this rectangle. This applies to all the rectangles. Where the rectangle connects to the curve, the x-coordinate there we call x asterisk. Some books would use a C or something else, okay? Depends on the textbook. And so the x-coordinate here is x asterisk in this interval, and here's x asterisk in that one, and so on. The area of a rectangle is the height times the width, okay? So f of x asterisk, that gives us the y-coordinate there, which would be the height. And the width is the delta x of k. Delta x is the distance from this x value to that x value. So there's your height, there's your width. Height times width, that gives you the area of a rectangle. This sum, 1 to k, adds up all the rectangles, all n of them between A and B. If we want our area approximation to be more accurate, we put more rectangles in. If we want our area to work out exact, we put infinitely many rectangles in. So this is an approximation. If we do the limit as n goes to infinity, then the area is exact. And this limit is what integrals do. Okay? That limit is what integrals do. This integral sign is an elongated S, which stands for sum. Sum. This is a sum. All right? We have to do something like this for that in polar. Now, before we do that, I want to remind you, this is different. This is not part of this discussion here. So this is its own thing here. Back in trigonometry, you likely we're given a formula for the area of a sector. This is a sector, okay? And the area of a sector is 1/2 r squared theta. You guys remember seeing that formula in trigonometry? You do? Let's have a quick little discussion about this. In a circle, there's your radius. If you travel along the arc of the circle, a distance equivalent to 1 radius, the curved distance is the distance of the radius, and then come back. That angle formed in there is a radian. That is 1 radian. That is the definition of a radian. All right? This is not part of this discussion. Well, it's going to lead up to that, but you're not going to be held responsible for this on an exam. I just want you to understand this stuff. Now, if we want to know how many radians this angle is, we have to count how many radii fit on the curve of the circle from there to there. So, if the radius here is 2, and this distance along the arc, which we call S, is 6, then that means 3 of these radii will fit on there, correct? So this angle in radians is 6/2, which is 3. So that angle is 3 radians. Everybody cool with that? So the definition of a radian gives us this. Theta equals S, that's the arc length, that's the distance along the curve, over R. That gives us the central angle measured in radians. All right? Now, if we multiply each side by R, we get S equals R theta. So actually, let me erase those R's up there. I'll keep that here. So this here is a radian definition. This definition of radian, the arc length divided by R gives us how many radians the central angle is. This is a arc length formula here. Okay, let me think. I wasn't planning on explaining this. Give me a second. The circumference of a circle is 2 pi r. Okay? This is S, this distance along here. The fraction of a circle that this sector is S over 2 pi r. This distance divided by the distance all the way around is the fraction of the circle that sector is. Does that make sense? That ratio of this distance, the arc length, divided by the distance all the way around, that's the fraction of the circle that is. Well, S, we just said right here, is equal to r theta. And then these r's can cancel out, and we have theta over 2 pi. So that angle over 2 pi is the fraction of the circle this piece is. Now, what's the area of the circle? Pi r squared, right? Correct? So if we want the area of this sector, this is the area of this sector, we take the fraction of the circle it is, and we multiply it by the area of the circle. Oh, that's just pi r squared. So the fraction of the circle this is, times the area of the circle. The pi's cancel out. The 2 in the denominator, that gives us the 1/2. And you got the r squared, and then you got the theta. That's where this comes from. Get the area of the sector of the circle. You guys got that? That's where that comes from. So now you can believe it. We're going to be using that over there. Okay?